momentum, momentum of object about its own mass center. Okay, so it kind of has two different components. That's what the Hg is, and then this part right here, this is the angular momentum of mass about point. That's one of the big findings when you go through this. Like I said, I'm gonna skip a lot of the details here, but this is one of the big findings here. This is trying to point directly at Hg. Right? Hg is the angular momentum. So if I want the total angular momentum of a spinning body about an arbitrary point O, I would figure out how much angular momentum do we have of the object spinning about itself. So it'd be this pencil kind of spinning like this, right? That has angular momentum as it's spinning. But not only that's the Hg part is its own thing about its own mass center, but then it's also moving. If it's moving like this as well and spinning, the second part of it is the angular momentum of that center of mass about the arbitrary point O. Okay. So if it was going like this, if I said, what's the angular momentum about this point right here? It's spinning like this, right? I would say, how much angular momentum does it have about its own mass center? And then I would do an R cross MVG part that goes about that. That's the second part of it. So back up here, I guess the drawing I have, if this thing was spinning about its own mass center, there'd be how much is it spinning about its own mass center plus this angular momentum associated with that mass center moving around it, okay? Big finding as we step through this thing. All right, then we come down, we haven't defined what Hg is. Let's look about how do we define the angular momentum of an object about its own mass center. Okay, what you do is our angular momentum term was just R cross MVG. And basically what we do is we just sum that up for every one of these like little miniature differential blobs here. So we're gonna be an integral involved, right? So that's what this is, R cross mv, right, is what the angular momentum is, and this is what it would look like in differential form. Okay, this velocity right there is just going to be omega crossed with r as seen from g, right, and this is everything's traveling in a circle, right, so this is just r cross omega, or omega crossed with r, that's the circle part, right. We're going to simplify this down to simply 2D problems, right? With 2D problems, right? This would actually stand true for 3D problems as well, but in 2D problems, we're just gonna say all of our rotations are gonna be about the k-axes, right? Also, all of our dimensions here are gonna be in the x and y direction, right? Because it is just planar, we're dealing with planar, it's just stuck to the wall like this. 3D gets more complicated than this, but when you make those assumptions, right? And I substitute them in up above, right? This omega, that omega goes into there. This dm is seen from g goes into here and goes into here, right? And when I do that and I carry out that integral and I pull out everything that's constant or it isn't affected by these things, what I get is this. Right? What I get is this. My angular momentum about its own mass center is this, where I integrate this x squared plus y squared dm. And this is, if you think of this things, right, the Pythagoreans, x squared plus y squared is just r squared. It's like this. It's the what's that thing? Hypotenuse squared, right? We could write this slightly different, and this is what we got right here. X squared plus y squared is just r squared, right? And then does this look familiar in any way? R squared dm. What's r squared dm? Oh, Jermaine, what we got? We just did that on the right before we got into here. R squared dm. Mass moment of inertia. Good. That's good. That's the mass moment of inertia. Okay. I like that game, right? Mass, moment. That's the mass moment of inertia, that R squared dm. Good thing we covered that. We know what that is, right? We just went over that. We looked this mass moment of inertia up, and so that's just IG, okay? And so then that's what our angular momentum of an object about its own mass center is just Ig times omega, okay? And then it has a direction associated. Hg has a direction associated, and it's in the k direction because omega is in the k direction, right? Big finding there, right? That's one of the things, that we did there. You did something similar for area moment of inertia and how it's related to bending. If you haven't, you're going to do it really soon, right? My over I, right? Or sigma is equal to my over I, or sigma times I is equal, right? That it's going to be something that comes up. You did something similar where you went through and you did some, and then this thing popped out what the moment of inertia was. And same thing happens here. You kind of substitute things in there. So that's just part of it, right? So if I want the angular momentum of an object about an arbitrary point, right? I do this part right here. This is the angular momentum of the object about its own mass center, and then I add on to it how that the angular momentum of that mass center is about an arbitrary point. So it has both of those things, the spinning part and the translating part, and how that translating part has angular momentum. Okay. Now another big, so that's just a general. Right, this is if I'm doing angular momentum about its mass center, I use that one. If I have an arbitrary point, I use this one where I have the mass center and this other part. But if I can also write this slightly different, right? If you applied the parallel axis theorem, you could get to this conclusion as well. If I just calculated, if I was after this arbitrary point O, if I calculated the moment of inertia about that arbitrary point O, then I kind of get rid of this R cross MVG part, and I could just use the IO times omega, okay? And again, we're not to moments yet, but when we get to moments, that's going to be a big distinction. If I sum the moments about the mass center, I'm going to use IG. If I sum the moments about an arbitrary point, I'm going to use IO, right? And then the way you make the jump from here to here is with the parallel axis theorem. The book kind of goes through that. All right, so we're not there yet. Right? We need to tie this to moments. Right now we're just talking angular momentum at this point. We need to tie it to moments. We're going to follow a similar process that we did for particles. Similar process. Again, this is going to be one of those ones where I go through quickly. I'm just going to jump to the key parts. Key parts. Let's see what the key parts are. So it's all based on taking the derivative of the angular momentum. Take the derivative of the angular momentum. Dot. What do I want to talk about? I want to talk that there's a missing M right here if you really wanted it. I don't know where that went, but that belongs there. Let me go through, substitute in, blah, blah, blah. This is for particles. Just to make it clear. I want to get to the good stuff. All right, this is a big one. I'm still not quite there. This is the real big one. This is the one I want. Clearly. Okay, I mean, if you really, like I said, the book's got more details on there. It's so boring to me. I don't want to talk about it, but this just goes through and it just steps through and does some substitutions along the way, and then makes them like, oh look, dvg dt is actually the acceleration, and you substitute that in, and then you just keep working your way down, and it's. We apply the same theory that we did for particles. We apply a similar process to get to this, and so that we're almost there. The sum of the moments about O is the derivative of HO about an arbitrary point plus V times MVG, and then we make a couple more substitutions, and we get to this, right? So that's the real big one, okay? So to get to this one, it is sum of the moments about an arbitrary point O is equal to the derivative of the angular momentum plus R crossed with MAG, okay? That guy right there. But we could simplify this down even more. So let's talk about these ones. Right, this is the most general form. This is just the same one repeated from above. The general form of my moment equation. We're gonna simplify this down significantly. Right? There's special, so that's the most general form. If you had a more really complex thing, this equation is the one that you would use. But we're gonna deal with special cases. That's the only thing we're gonna do in here is these special cases. Right? The special cases we're gonna deal, first is planar. That one up above there, this counts for 3D and everything. For special cases, for planar, this AG, or HG rather, is just IG times omega. And if I take the derivative of that, right, I need the derivative of it, I need HG dot. If I take the derivative of this, IG is constant, so it comes out, so it's just the derivative of omega, which is just alpha. So that HG dot component is just IG times alpha. So if you have a case where it's just planar, you would use this equation. Right. There's our first moment equation that we're going to use, right? But just to flash back, what we're trying to do is get how do moments relate to alpha, right? How does it relate to motion, right? And here it is. Here's our first one. If we have a planar case, and I have an arbitrary point O, I can figure out I could sum my moments. They're going to come from a free body diagram is equal to IG times alpha in the K direction plus this additional component, right? This would be a case absolutely arbitrary, it'd be spinning and translating about a certain point, and you would calculate the total. You'd sum your moments about the total object or the whole system rather. It's IG times alpha plus RG is seen from O crossed with MAG. Right? We're not going to use this one very often. Sometimes this one comes into play. This is just an arbitrary point that doesn't have a fixed point. Okay. The other one that we're going to use quite a bit. These are the two that we're going to use quite a bit. If you have a fixed point, right? What do I mean by fixed point? Well, our example, this one, right? This would be rotations about a fixed point, right? This thing is rotating about this point right here. That's a fixed point, right? If I have a case where we have a fixed point, then I could use this equation. Some of the moments about O just becomes IO times alpha. Right? And that just comes from our previous thing. We said that our angular momentum about O was just IO times omega. I just take the derivative of that. I is constant, so then it just ends up being this. Right? So that's our second equation. Right? And then our third equation, if we have a mass center, so if we're summing the moments about a mass center, then it just becomes IG times alpha. Basically, this second part goes away because RG is seen from G is 0. And so this part just goes away. And so you're just left with this. Most of our cases are going to be this one and this one. Right? This one or this one. I don't think, maybe one, you have an arbitrary point, this guy, but most of them are these guys. Right? Now, it's important to note you only get one of these, right? You get up to three force equations. In 2D, we just get two force equations, X and Y, and then we only get one equation out of this. You either have a planar general case around an arbitrary point, or a fixed point O, or a mass center. You don't get multiple equations here. You just get one. One of these you get to choose, right? And it all just depends on the type of problem. Okay? All right, let me give you a procedure. And then we'll do an example. That's what I'm trying to get to is the example. Okay, I always have a step 0 and I call it mass probs. Right? You might have to calculate mass properties. What do I mean by mass properties? I, what the mass center is. Yeah, usually that's what it is. What I you're going to use and what it is, and then where the mass center is. Right? We need to know where the mass center is because that's where our force equations act through. Okay? I guess I can add that to it. Mass center and relevant. Right. Okay, I always call that step 0. Right. Free body diagram. Super important in these problems is that free body diagram. Same process for making the free body diagrams last. It's just now it's more complicated because our object is no longer just a point, right? kinematics as required. Okay. I need to know what AG is. This is usually kind of what I aim for. I need to find out what AG is, what alpha is, what omega is, and how they relate. And how they relate to each other. We'll do an example. You'll see how it all plays into fact. What ends up happening is you'll have too many unknowns, right? You're gonna have too many. You're gonna have alphas unknown, and AG is unknown, and forces are unknown, and moments are unknown, and there'll just be too much, right? And so we have to constrain the problem some, and that's where kinematics come in. We just add in the kinematics, and then it relates everything, and then it enables us to solve it. Okay. And then we're gonna write down equations of motion. Or just EOMs. Okay. Equations of motion. We get 3 per body. Two force equations. And 1 moment equation. And this is per body too. So if you have a system of bodies, you get 3 of these per body. Fourth, solve. Okay. This process you should be used to, right? This is the same process we did for particles. It's just now we've just added in this extra moment equation basically, right? And the concept that those forces are mass times acceleration. Okay. Everybody cool? Cool. All right, so what do we do with this? All right, just a summary again. I was just write these down. Here's our. We get 2 of these guys, X and the Y, and we get 1 of these, just to make it clear. Every semester, people write down all 3 of these when they're trying to solve these, not thesis. Okay. Just 1 of them. Just depends on what type of problem we're dealing with. Okay. Highlighted. Please don't write down all 3 of them in your solution process. And then you have too many equations and not enough unknowns if you do it that way. Okay. So then let's do a problem. That's what I want to do. That's what I sped to. Like I said, if you want more of the derivation, you can read through the book. There's the whole thing, step by step. Or you can just trust me because I'm a doctor. I know that's what it's a bad way to do it. It's a bad way. I just don't like it. It's just dry working through the vectors and stuff like that, but it's a bad way. But you can. I'm pointing you to the direction. You should go see what they did. No, go see how they stepped through it. I think it's worthwhile. Okay, except for it's not worth taking class. I want to do these examples. Okay, so we have 2 identical slender bars, each 5 kilograms, each length 1 meter, are welded together in the shape of an L, as shown. So it's shaped of an L. One end is pinned at A. Okay. If the bar is released from rest in this position shown, find the angular acceleration of the bar at this instant and the reaction at A. Right. And so this is not a statics problem. You can't just sum the forces equal to 0, sum the moments equal to 0, because they're not equal to 0. They're equal to mass times acceleration and I times alpha, right? So we have to include both of those things. So let's go through this. Step 0 was mass props, right? And they didn't tell us where the mass center was, so I need to find out where the mass center is. Right? I need to determine where the mass center is. I also need to, oh, come on. Motherfucker. All right. I knew it was going to do that. All right. Mass props. So I need to know where the mass center is. Oh, I could say that here. Center and I. So to determine the mass center of this, right, our definition of mass center is just a weighted average. I pick a reference point. Right? I'm going to make my reference point be right here. And that's going to be a reference point. And so then I'm going to figure out what the x bar is relative to that point right there. So the first bar, this thing is length, what is this thing, length 1? Is that what it is? Length 1. So this is going to be 0.5 to get to here. Right? So it would be negative 0.5, negative 0.5, times its mass. They said each one was 5 kilograms, right? 5 kilograms? Yep, 5. And then this guy, this object right here, its distance in that direction is just 1. So it's minus 1 times 5. And all of that divided by the total mass, which would be 10. And so this ends up being negative 0.75 meters. Do that same thing with the y bar. The y bar, the distance of this guy to in the y direction is just 0, right? Because it's at the same level as that. It'd be 0 times 5. Oh, this is a plus. This is a plus right here. Plus a negative. That's a plus there. Plus negative 0.5 times 5, right? Because now I'm going this direction, and so that's negative 0.5 is the mass center of this one. And that divided by 10. And this ends up being equal to negative 0.25 meters. And so what does that tell us? That tells us that this is where our mass center is. Negative 0.75 there, and 0.25 here. Right. This is one of the first steps I always do, is just find that mass center if it's like a big object like this. As we've broken up into components. We need that later when we do our kinematics, right? There's that MAG component. Okay. The next thing is, right, and at this point, I can make the decision of where I'm going to sum my moments about, right? It's really, you could do it about the mass center. I could sum my moments about the mass center. I could find what I is about the mass center. I could sum my moments about the mass center. And if I sum my moments about the mass center, then I need IG. I need I about the mass center if I'm going to do that, right? Or I could sum the moments about this fixed point over here. And if I sum the moments about the fixed point over there, then I need I about the fixed point, right? You can make the decision to go either way. Is one way better than the other? I don't know, right? It'd be similar to like tilting your axes, right? Sometimes it makes it easier, sometimes it makes it more difficult. Sometimes it's worth it, sometimes it's not worth it, right? So in this case, when we think about summing moments, right? Well, you know, this is going to have obviously the mass times gravity acting through the mass center, and then it's going to have reactions that look like this, right? And if I sum my moments about here, then I have to take into consideration my reactions because they're going to cause moments about the mass center. So my reactions will show up in the equation. If I pick my fixed point to sum my moments about, then I only have one term, and it's this gravity term is causing a moment about the mass center. And then these reactions aren't in that equation because the moment from the reactions about a fixed point are 0. So in this case, it is a little bit easier to do it about the fixed point. Either way works though, right? It's just this one, if you do it about the mass center, you're after these reactions, then they end up being a coupled equation. The force equations and moment equations end up being linked together, and you have to simultaneously solve them, which is totally fine, especially with our TI-89s and Inspires, right? You're doing all right, Mark? You okay? Should I keep it down? Should I keep it down? It's okay. It's okay. I've been there. You were doing it okay. I had this one student, Flynn, who you may know or get to know at some point. She would fall asleep like this. Her mouth would fall, her head would fall back, her mouth would open. And then it was like, come on now, come on. Don't do that. That was too, 2 tenths. Okay, so let's get I about A, right? I about A is the fixed point. We've just decided, we've decided to do it about there. Maybe we'll do another one later where we do it about the mass center. I can show you what I mean by M Lincoln. So, all right, so I want I about A. So then this, right, there, you can't find an L shape in the book, and so then you have to do the parallaxis theorem to get there. I'm seasoned with my parallaxis theorem, so I'm gonna do it pretty quick. All right, I about A is going to be equal to I1 about A plus I2 about A. So I got to get each one about A. I1A is just going to be, right, so this is, I'm going to call this, did I do that 1 and 2? Yeah, this I'm going to say object 1, and this I'm going to say object 2. I1 about A, I can look, that is actually in the book, right? That's the moment of inertia of a slender rod about its end, right? That's ml squared over 3. So I could just go straight to that. Right? M there is 5. 5. L is 1. Add over 3. Right, and then I2A, we can't, that is not in the book. So I have to do the parallaxis, which is ml squared all over 12. That's the object's moment of inertia about its own mass center. And then I add on to it md squared. Okay, so I'm going this guy, that's an axis, and that's an axis. Okay, and this is just so I just want to show you, so I'm trying to get this object's moment of inertia about this point over here, A, right? And so I do a moment of inertia of the object about its own mass center, that's this, ml squared over 12, and then it's plus this md squared. That d is this distance right here. It's that distance. Right? This is, from years of doing this, people kind of messed that one up. Oh, that's just d, rather, not d squared. Right? The reason that's d is because you think about the axes. You got one coming out, right? That's that axis, and it's parallel to the axis that I'm trying to get about, that A over there. So there's 2 parallel axes. I want the distance between those 2 parallel axes, which would be that d, that direction. Okay? Trying to visualize that. Just picture the axes coming out of the board, and you want the distance in between those axes. People kind of sometimes go that distance, or they do that distance, but it's actually that distance straight across there. That d squared is going to be equal to 0.5 squared plus 1 squared. Right? So it's just, this here is 1, this is 0.5, so it's 0.5 and 1. It's 0.5 squared plus 1 squared is what that d squared is that 1.25. I'm just going to leave it as d squared right there, right here. Draw an arrow here. Beep. Right, that's at 1.25. And lo and behold, this ends up being equal to let's jump. This ends up being equal to 5 times 1 squared all over 12 plus 5 times 1.25. I don't actually calculate what that is, but I do calculate what the overall is. 8.33 kilograms meters squared. For some reason, I didn't write that. I didn't write what this actually equaled, but I did add them together. So there's our mass props. Kind of a boring step, but important to get it. The key things there was I needed to figure out what where the mass center was, found it, it's right there. And then what the I was, first what I to use, and second, actually calculating it, and had to use the parallaxis theorem to calculate it. Okay, got it. All right, step one, more interesting stuff. But we're set ourselves up. Like, could you wait to do that step? You bet, right? You could go along and then eventually you would go like, oh my God, I need to know where the mass center is. And also I need to know what my eyes are. You could do them in any order, as long as you hit them. That's why I said sometimes think of these things as check marks rather than steps. A checklist. Free body diagram. Okay, free body diagrams, we now have to draw the whole thing. Right? You can't just draw a dot anymore. Oh, wait, no need to be so small here. Okay, I'll blow it up a little bit. Okay, there's our free body diagram. Force is acting on this thing. What we got? Gravity, good. Yeah, there you go. Gravity acted through our mass center. Right? I'll just say that it's there. I mean, we know exactly where that's at, but we'll, right? What's nice is I know my mass center. I know that that's what gravity acts through. Could I do this and say, oh God, and say that, oh, I got that mass times gravity and this mass times gravity? Absolutely, right? You could leave those things as being separate, right? But, you know, it's nice to be able to use the actual mass center of the overall thing. Just makes your life a little bit easier. So that's the total mass. But I could just say, well, there's that guy's mass and this guy's mass. Absolutely, the same thing works. It's just you have more things would show up in your moment equation later on. But that's totally fine. Okay. What else? The reaction, right? So I've got this guy. Again, I don't know which direction they're going to be going, so I always just assume positive. Right? AX and AY, the reactions over there, right? And, right, the other components that we want on here is any dimensions that are important. There are some important dimensions. There's this guy, where that mass center is. That's 0.75, and then that distance there is 0.25, right? X and Y direction as well, which were kind of implied with our reaction over there. So which way is X and Y? But you could put a little X and Y here just to make it clear. X and Y. Our coordinates are. Those are my free body diagram. Not much happening here. Right? But it's important to just write it all down. It makes your life a lot easier when we get into the rest of this. 2, equations of motion. Nope, kinematics. When I solve these problems, what I usually do is I just say, right, at some point, I'm going to need to know what AG is, right? And so I say, all right, I'm going to step to AG. Just like, you know, our kinematics problems, right? I want AG. I need to know AG. So I think to myself, all right, I better go find AG, right? I know eventually it's going to be related to omega and alpha and stuff, but I'm just going to I want to take a step from here, because that's a point I know something about, right? The acceleration at point A right there is 0, and I'm going to take a step out to G, okay? And you just use our kinematics that we just spent lots of homework doing. And this is an easy one for you, right? So I say AG, I need to know what AG is, right? That's going to be equal to AA plus alpha crossed with R, G is seen from A, minus omega squared, R, G is seen from A. I write down my kinematics equations just like that. Right? So we're going to use those things the same way we did it before. It's just now I'm going to take a step to AG. AA is 0, right? Because it is a fixed point, so AA is 0. Right? And then this thing, the problem statement says, well together, the bar is released from rest. So that means it's not moving at this instant right here, which means omega is 0. Right? Then omega is 0, starting out at rest. If it had an omega, we would leave it in there. But in this case, it's starting out at rest. G, yep, there's a little G. RG is C from A. Right? So then just keep going with this. Alpha is in the K direction. Always just assume it's positive. I'm going to cross that with RG is seen from A. That's negative 0.75 in the I minus 0.25 in the J. Right? RG is seen from A, that dimension right there. So it's negative 0.75 in the I minus 0.25 in the J. And what you get this ends up being equal to 0.25 alpha in I minus 0.75 alpha in the J. Okay? That's what we get. So this component right here, that is AGX. And this component right here, since it's in the J direction, is AGY. Oh, that negative is part of that too. So we need those later on, right? AGX and AGY, and there they are, right? And so I always just do that, right? Am I missing a negative? No, what's the AGX? Oh, if it's a positive alpha, you're right. We're assuming it's a positive alpha. Is that right? Did I do so? Positive alpha. Positive alpha going like this. Yep. Okay, I'm good. Okay, yep, I'm good. Okay, right. Next step 3 is our equations of motion. How much time we got? Oh, we got 4 minutes. Right. Equations of motion. Let's get a couple of these down. Sum of the forces in the X is equal to MAGX. Would you look at that? I just found what AGX was. So that's good. Right? So then what I do is I look at all my forces in the X direction. So I just come up here and say, what's acting in the X direction? And all I got is AX. That guy right there. So that's what I write here. AX is the only force that I get, and that's equal to MAGX. And we just figured out what that was, and that was just M times 0.25 alpha. Yep, 0.25 alpha. Okay, I just figured that out. Right, that's just this right here. Whew. Okay, then I write my next equation of motion down. Sum of the forces in the Y. And the Y is equal to MAGY. I look in the Y direction. What do I have? I've got MG and I've got AY. I got positive AY minus an MG. That's equal to MAGY. I just determined what MAGY was. That's just M times negative 0.75 alpha. And so I'm out of force equations. There's nothing going on in the Z direction, so I need my moment equation. I'm doing my moment equation about a fixed point. So sum of the moments about A is equal to I A times alpha. Right? And so then what I do is I come back up here and I look to see what kind of moments do I have about point A. Well, I've got mg times 0.75, right? And is that going to be a positive moment or a negative moment?
Positive.
Positive, right? You take the direction that it's going, which direction is your thumb going? My thumb's coming out like this. That's a positive moment. So this is going to be, this is going to be mg times 0.75 is that moment arm. It's positive, and that's equal to IA times alpha. Okay? And so, okay? This also, if you wanted, sometimes it's helpful, right? this is just going to be R, G is seen from A. That's the moment crossed with F. Sometimes if it's complicated, it's nice to use that. If you remember in statics, that's another way to do it. Okay? So if I would have summed the moments about the mass center, totally fine to do. But when I got to this step, summing these moments just wouldn't have just one term. It would have IA times that distance plus IX times this distance, right? It would be in your moment equation. And then the moment equation would be linked to your other two equations. This one, you could directly solve for what alpha is. But there it is, right? So we have 3 equations and 3 unknowns. Just to identify the unknowns, right? I do not know what this reaction is. That's what I'm after, right? I do not know what AY is, right? That's what I'm after. And I don't know what alpha is, right? And so there's my 3 equations and 3 unknowns. And you solve this thing for those unknowns, right? In this case, it's pretty easy. You solve for alpha, you take the alpha and you put it in the other 2 equations, and then out pops your answer, okay? And so then, or you put it in your calculator just like those, and that's what I did, and I got alpha equal to 8.83 rads per second squared. AX is equal to 22.1 newtons, and AY is equal to 31.87 newtons. Okay, which is not what you would get in statics, right? In statics, where the hell would you get an AX, right? You wouldn't get an IX, right? There are no forces acting in that X direction, right? There's no forces acting that way, but we do pick up an AX, right? And what that's from is the centripetal acceleration, right? That if you look back to where that actually came from, it came from centripetal acceleration. Did we have to pay attention to that? No, we didn't have to pay attention to that because the math took care of that force, but we can come back and, right? So this, if you release this thing, there would be a force that direction of 22.1. There'd be a force that direction, which would be equal to 31.87, which is less than just gravity itself. Right, so this AY is not just how you solve it in statics as well, right? So we end up with the reaction in the X and the Y direction right there, and from the centripetal acceleration in the other part too. Cool beans? And so all the problems are just like this, right? They're very structured, they're very nice, well laid out, but then obviously lots of room for mistakes. You can make mistakes in calculating your I, you can make mistakes in doing your kinematics, and then obviously then the solving systems of equations. Some of you are terrible at, okay? I mean, I swear to God, that last exam I graded, 90% of the errors that came about was algebra between the start and the finish. So please, for the love of God, either learn how to do algebra or get a tool to help you with it, right? Has anyone bought a new calculator and regretted it? No, you have not. I know if you do say you regretted it, that you're a liar. You're a dirty, rotten liar.